but it will make a lot of sense. It's step by step, and it's used in language that you actually understand. So I like to think of it as it covers everything that you need to know about that topic. And of course, I have timestamps throughout every single video to help guide you understand, what you need to learn. The new thing that we have added here, and Cooper is part of this, is the new chapter reviews. These are Cooper's project that we've been working on this entire summer. And I want you to think of these as a quick way to just review on that chapter. So it is perfect for studying or cramming for an exam, which I know happens. So we have 14 new of these chapter reviews. That's everything that's included in the basic plan. And then, of course, these videos are also included in the pro plan, which is the middle plan that we have on community. So besides the lesson videos and the chapter reviews, we also have practice problems, study with us, practice exams and finals, an AI tutor, and video commenting, which I'll explain what this all means. So our practice problems are different levels. So we do have 3 different difficulty levels that you can see for every single chapter. And it also comes with a PDF, a downloadable PDF, so you can follow along with the video and then double check your answers. What's also included is our Study With Us series. As many of you may or may not know, this is a series that I did with an OCHEM student for both OCHEM 1 and 2, where it's pretty much a guided study session and you get to see the study session. So any of the questions that you may think, is anybody else having this question? I'm a little nervous to ask that to my professor. Well, she pretty much asked them and she asked them to me. So I answer those questions on camera. And I honestly think it just makes it a lot more fun and less lonely, because I know studying can feel lonely at times. So you get to watch that. And our practice exams and finals, which you'll notice, we partnered up with Professor Dave, and he also created some practice exams. I also have my own set of practice exams and finals. So either one of those you can take. We also have an ACS exam for those of you taking that at the end of the year. So that's also helpful. That's included in the pro plan. And we also have our AI tutor, that feature that we added. So this is for 24/7 help, which I know that it happens at midnight sometimes when you are just freaking out before an exam. So this is a quick way to make sure to get those questions answered. And it also will recommend a video that we already have on community. Another thing, part of the pro plan, is our video commenting. So you can comment a question. Let's say you didn't completely understand what was happening in the video, or you need clarification on an example. Then you can ask your question. We have different subject experts that will then respond and guide you on answering that question. And then the premium plan, which is something new that we added, and again, Cooper, who is here with me, is the main one who's going to be leading this. So the added feature for the premium plan, besides everything that we already said, was what we have today, the weekly live tutoring for both OCHEM 1 and 2. And Cooper is going to be the main one who is leading this every single week. He's going to be guiding you, helping answer those questions. And what you get from this is you're going to get a private channel to be able to post your questions ahead of time so that Cooper can answer them on the live tutoring session. And he's also going to be going over any sort of tips and tricks that he has to help you prepare for your exam. Plus, I want you to think of this is literally weekly live tutoring for the cost of like one session for a private tutor. And you instead get this at such a small price point. A tutor charges by the hour, while the premium plan and community will support you every single day of the month. So that's a big added feature that we have this time around. So definitely utilize it. And the other thing that I wanted to mention was this is how you can see the video categories, select what you're looking for to quickly find whatever video that you need. We have so many videos, my goodness, over 200 now, and we just keep adding on and on. So wanted to share that with you. Now that you know that, I'm going to let Cooper connect and do all the things that he needs to do. And while he's doing that, I want to give a formal introduction now that you guys are on. This again is Cooper McIntyre. He is a new instructor that we added to the community team, and we are so excited that we met and that we can finally start this off. So I'll hand it over to him and go ahead and kick it off.
Perfect. Well, hello everyone. Nice to meet you all. First and foremost, can we all see my screen? Perfect. Think that, yes, I got a thumbs up. Appreciate it, T. But yeah, hello. My name is Cooper McIntyre. If you don't really know who I am the founder of Catalyst Chemistry, which I started around a year ago just as a gateway to allow students to become more confident in organic chemistry and to easily help them every single day through social media, daily practice problems, whatever it may be. But in terms of you getting to know me personally, in terms of my background, I went to Ohio State and I had a degree in cellular molecular neuroscience. And as we can see, I shifted gears a little bit, wanting to tutor organic chemistry. Yes, I was a nerd and I loved it a little too much. And then one of the things I wanted to let you guys know is that I've been in your shoes. Melissa has been in your shoes. We weren't just born with the knowledge of organic chemistry. We had to go through those extremely late nights and those long, strenuous study sessions to get where you want to be. So if you have any questions in terms of how to study, in terms of if you're nervous or anything like that, feel free to leave it in the chat and we would love to be able to talk to you about those. And then in terms of some fun facts about me, just so you don't view me as just an organic chemistry nerd, I love rock climbing, love being outdoors, whether it's indoor rock climbing, outdoor rock climbing. I enjoy being outside. And then I'm also a zipline tour guide, which many people don't really know about me. So during the week, I am an organic chemistry tutor. But then when it comes to the weekend, I am a tutor of the trees that I like to say. And then also, if anyone loves cats, I have a one-eyed calico kitty, and this is Sedona right there. So feel free to just admire her beauty. But besides that, that was a little bit about me, and we're just going to jump into it since we already started. And in terms of this week's topics for our introduction for Organic Chemistry 1, we're going to start with the fundamentals, just reviewing some of the atomic structures in terms of just what an atom is, just so we can have all those building blocks in terms of what a molecule is. And then we'll also have a slight review of bonding, making sure we know how to find electrons in terms of our bonding and non-bonding electrons, a lot of those basics, which will lead us into the main portion of our lesson today, and that is Lewis structures. Now, in terms of Lewis structures for today's lesson, we're going to go over how to draw them, and then also how to find formal charges with them. If you know how to draw Lewis structures and you're super comfortable with finding formal charges before day one of organic chemistry, you're going to be light years ahead of most students. And if you stay tuned for next week, when we go over bond line notation, you're going to be about a month ahead. So feel free to stick around. And then we'll also go over condensed formulas, which may be a new concept for some of you. I know a lot of us are used to a different thing, but we'll go over what those are. And then finally, we'll finish everything up with polar covalent bonds, talking about electronegativity, reviewing what it is and how important it will be. And then also we'll dive into induction, but before we get going with a lot of the concepts in terms of what I want to go over, I do want to touch on the difference between general chemistry and organic chemistry, because I will tell you, they are completely different classes. General chemistry, I don't mean to bring up any horror stories or anything like that, but Gen Chem is math heavy. There's a lot of equations you need to memorize, and it kind of feels like just a plug and chug class where you're just plugging in numbers into an equation that you had to memorize, and that's how you get the answers. But fortunately for organic chemistry, there's not that much math. There may be like two or three topics where you have to know some equations, but I promise you it's not that bad. Um, for another difference about general chemistry and organic chemistry, Gen Chem is memorization heavy. If you were to just use flashcards and you memorized everything in organic chemistry, you definitely had a shot at doing very, very well. But when it comes to organic chemistry, I will warn you, it deals a lot more with understanding. I promise you, you don't want to just solely memorize every single thing. Take the second and the time to understand the material because come exam time, it's a lot more about applying the information as opposed to just recalling it. And then finally, general chemistry has a lot of standalone chapters. And what I mean by that is just say if you did very well on chapters 1, 2, and 3. Chapter 4, you had some difficulty on, you just skipped it. And then chapters 5, 6, and 7, you did really well on. You could do that. But for organic chemistry, each chapter builds on each other. That means, for example, chapter 1 builds on to chapter 2, and it's just a continuous cycle all the way until the end of OCHEM 2. So just make sure that you're not leaving any information behind and that you're trying your best to keep up with the new information. And that's why Melissa and I are here to help you stay ahead. Um, and then if this is your first time taking Organic Chemistry 1, you've probably heard all the negativity about organic chemistry, and you've probably heard a lot of quotes such as, "Oh, like I didn't do well in Gen Chem, I must be doomed," or "I heard organic chemistry will ruin my GPA and I won't get into grad school," or someone has probably may have told you just might as well drop out already for taking OChem. But there's one thing I want to tell you, and that's to not listen to the haters. Just because someone else did bad or just didn't do well in organic chemistry doesn't mean you will. The one thing I like to tell my students is imagine how much easier organic chemistry would be if not everyone talked bad about it. So go into this with a fresh mindset, and that's what we're here for, is to help you walk into organic chemistry feeling confident. And then finally, before we jump into the material, I want you to be honest with yourself. Now, what I mean by that is constantly assess how you're doing in the class after every quiz, after every exam. And if you need to change something when it comes to your studying habits, feel free to change that. I know there's a lot of YouTube videos of like the best ways to study, but in my opinion, the best way to study organic chemistry is the way that works for you. So just be open to try a bunch of new methods or whatever it may be. But from there, I want to go ahead and just dive right into the material. And the first thing I want to review is just a simple atom in terms of what's involved with an atom, what everything means. And first and foremost, we'll review what protons are. And those are going to be your positively charged particles that define an element. Now, in terms of it defining an element, what I mean by that is we'll take carbon, for example. Carbon, as we'll realize in organic chemistry, is the most common element. And carbon, for example, just has 6 protons. Now, say if we were to grab a single carbon atom and we were to add an additional proton into there. Instead of carbon, we would now have nitrogen because it has 7 protons. So just be aware of changing the protons will change the actual element that we're talking about. In terms of neutrons, we don't really deal with those as much in organic chemistry, but if you remember what they are in general chemistry, neutrons will be those neutrally charged particles that are found in the nucleus of an atom. And in terms of the nucleus of the atom, it's going to be in the very center of the atom, and that contains both protons and neutrons. And since we have those protons, overall, the nucleus itself will have a positive charge. And then finally, we'll be dealing with electrons, and those will be your negatively charged particles that surround the nucleus. And the main electrons we'll be worried about are those valence electrons all the way on the outside, but we'll get to that a little later on. And then a simple way to put it, electrons will help determine your charge. Uh, the one thing I want to review real quick before we enter our first practice problem is basically what atomic size is. This is one of those periodic trends you probably reviewed in general chemistry, but atomic size looks at how large an atom is. And this will be very helpful when we start talking about more complex concepts later on in organic chemistry, which is why I want to review it now. But in terms of the periodic trend that we need to know is that atomic size will increase as we move from the right side of the periodic table all the way towards the left side. See it again, moving right to left, it'll increase. And then also, as we go from the top of the periodic table and we move down the table, it'll increase as well. And we'll go over why that is in just a moment. But for our first example, what I want us to do is to rank the following atoms from smallest to largest. So whenever I'm presented with a question that's asking us to rank an atom from smallest to largest, the first thing I want to do is, especially if we have a periodic table, is to find our elements on the table and just circle them just so we have a baseline in terms of where they are, and then that's how we can kind of assess how large they are. So for example, we have helium up here, oxygen here, lithium, tellurium, and then iodine. And now that we've circled them, we have a good understanding of where they are. We can now assess how small or large they may be. And like we said, with our trend, up here will be the smallest element that we have, which is helium, because it is at the far right and at the far top of the periodic table. So our smallest atom will be helium, and then from there, we need to find our second smallest atom. So what we can do is we can move down and we can see that the first atom we run into is oxygen. So we have to be aware that oxygen and lithium are in the same row on the periodic table. And if we were to look at our trend, our atom increases in size as we move from the right to the left, which means lithium will be larger than oxygen since lithium is all the way on the left side. So in this case, oxygen, and I forgot that the E on helium, but we added that in. So oxygen will be larger than than helium, and then from there, lithium will be larger than oxygen. So we have the majority of our elements taken care of, but now let's move on to iodine and then tellurium. If we were to look right here on the periodic table, they're right next to each other. But yet again, we need to look at the trend. Since tellurium is on the left side of iodine, tellurium will be larger, and that makes iodine larger than lithium. And then, like I said, since tellurium is on the left side, tellurium will be larger than iodine. Nice. Any questions so far on that? I'll give it a slight pause. Sweet. And then in terms of atomic size, right here is the answer. The reason we're increasing in size as we're going down the periodic table has to do with those valence shells. So as we're moving down the rows, we're increasing the number of valence shells that we have on the outside of our element. And as we're increasing those shells, the atom gets larger, which means our atom is just getting bigger and bigger as we add in more electrons. And then also, this is the main theme in terms of the rows, is that as we move from the left to the right side, we're decreasing in atomic size. And that's only because we're adding in more protons as we're going from the left to the right. And if we're adding in more protons, we're increasing the effective nuclear charge, and it's kind of sucking those outer electrons in closer to the nucleus, overall decreasing the atomic size. Move on from there. So after talking about atomic size, the main thing I want us to kind of go over are electrons. Now, electrons, yet again, are the negatively charged particles that surround the nucleus. And in my opinion, electrons will be one of the most important things in all of organic chemistry. You've probably heard the definition of organic chemistry 1,000 times, being the study of carbon-containing compounds and how they react, their structures, and all that stuff. But in my opinion, organic chemistry can also be defined as the flow of electrons. Once we get into a lot of the applications of organic chemistry, we'll see how the electrons are flowing within a single molecule, and also how they're flowing from molecule to molecule and how we're undergoing those reactions. So make sure as we keep on going through our sessions that we're always aware of where our electrons are and where they're going. And that's why we're doing this, so we can build that foundation. And in terms of electrons, when it comes to organic chemistry, the main electrons we're worried about are those valence electrons, which are the outermost electrons, which will participate in bonding, and they can also be non-bonding electrons. So let's see what that looks like in our next example. And for this one, what I want us to do is to count the total number of both bonding and non-bonding electrons in the following molecules. So we'll start with the left one most first. And the easiest way to do this, especially when we're talking about those bonding electrons, is just to count the bonds. And remember, yet again, the electrons we're trying to find are those valence electrons. So in terms of our bonding electrons, we'll go through and count the bonds. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 bonds, which means we have 26 bonding electrons. We'll go over why that is. So we need to remember each bond, so one bond equals two electrons. And a lot of the times in organic chemistry, whenever we're talking about electrons, they do come in pairs, whether they are bonding electrons or non-bonding electrons. So that's why we have two electrons. And then in terms of non-bonding electrons, that's where those lone pairs come in. So what we need to do is go through and count those lone pair electrons. We have the lone pair here, here, and here, which gives us a total of 3 lone pairs. And yet again, we have to remember that a pair of something means you have two of them. So one lone pair, sorry, has 2 electrons. So since we have 3 lone pairs, that means we have 6 electrons. And yet again, if you're confused about that, just imagine a pair of shoes. Pair of shoes has a left shoe and a right shoe normally. So that means you have 2 shoes per pair. Any questions about that first example? Sweet. Yeah, and then we'll go ahead and move on to the next example. And yet again, for bonding electrons, we'll go through, count those bonds. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since we have 10 bonds, yet again, each bond has 2 electrons. So 10 times 2 will be 20 electrons. And then in terms of those non-bonding electrons, we'll go through and count our lone pairs. So we have 2, 4, 6, 8 lone pair electrons. Any questions with that? Sweet, we'll just keep on going. And then right here is just kind of a review of what we just did in terms of those problems. And in terms of the bonds we'll be seeing a lot of in organic chemistry, and those are what are called covalent bonds. And covalent bonds are those bonding electrons being shared between two atoms. So we'll look at this covalent bond real quick. We have this bond between both nitrogen and hydrogen, and what that's representing is that these 2 electrons are being shared between both nitrogen and hydrogen. This bond is actually polar covalent, which we'll go over what that means at the very end of this session. That's basically when electrons are being shared unequally. And then the other types of electrons we'll see a lot of in organic chemistry are those lone pairs. And yet again, the lone pairs are a pair of electrons that don't participate in bonding. And for example, we have some right here. And the main thing I want you to realize with lone pair electrons is that they are isolated to a specific element or atom. And that's why they don't participate in bonding. So yet again, these electrons are isolated onto the oxygen, which is why they are lone pairs, as opposed to covalent bond electrons, when they're being shared, they aren't isolated to one atom. They're actually being shared between 2 different atoms. Move on. And then the last thing I want to mention in terms of electrons is we need to be aware of the octet rule. Now, whenever we're forming bonds, every single atom has a goal to reach an octet. And yet again, just to refresh your memory, an octet is when we have 8 valence electrons. Um, for example, if we're looking at this carbon, yet again, if we were to refer back to our previous example, each bond has 2 electrons. And if we looked at all the bonds around carbon, we have 1, 2, 3, 4 bonds. Yet again, 4 bonds times 2 electrons means we have 8 total electrons currently surrounding that carbon. So the octet is definitely filled. And then one thing I want to mention is a small exception, but we'll see this a lot in organic chemistry. It won't be one of those weird ones like general chemistry, but hydrogen only wants 2 electrons. And that's only because it just contains an s orbital, and its outermost valence shell can only hold two electrons. And for example, if we're looking at this hydrogen right here, it's nice and happy because it does have its two electrons being shared within that covalent bond. If you ever have two bonds coming off a hydrogen, definitely look kind of for a mistake and see if you did something wrong there. But now we are going to dive into the big bad of this lesson. Oh, I have a question. Sweet. So the question is, how does this info on bonds correlate to identifying sigma and pi bonds? Great question. In terms of now, I guess a very simple answer is the number of bonds we have can showcase either the sigma or the pi bonds. For example, when we have a single bond right here, that consists of a sigma bond. I won't go too much in depth on that right now, only because next week I do promise that we do have an in-depth review of kind of those sigma and pi bonds and all that fun stuff. But in general, in terms of helping us find sigma and pi bonds, it allows us to count the electrons very efficiently. And right now we're trying to become aware and being comfortable with finding those electrons so that later on we can easily find the sigma and pi bonds. But moving on to Lewis structures. So Lewis structures will be one of the big things we review when we first start talking about organic chemistry. And the reason we go deep into Lewis structures is because they lay the foundation for bond line notation. Now, if you've ever seen pictures of organic chemistry memes or just looked at a friend of yours who had previous notes, you probably see a whole bunch of lines and you're like, what the heck does that mean? The basis of bond line notation comes from Lewis structures. So we'll become comfortable with Lewis structures, and then next week we'll start to dive deeper into bond line notation so that we're comfortable with it before the semester begins. But I will say, in terms of Lewis structures, I always recommend having a set system or a set methodology, if you will, in terms of how we approach these problems, just so every single question you encounter, you're not kind of scrambling in terms of what you should do next. So for this one, we'll draw the Lewis structure of this compound right here. Now, in terms of drawing Lewis structures, the first thing I do is I want to count the total number of valence electrons and we'll then divide it by 2. Now, the reason we do this is just so we can be aware of how many bonding and how many non-bonding electrons we have. And then in terms of dividing it by 2, that allows us to easily check our work later on. So what we need to be aware of in terms of counting our valence electrons is how many valence electrons each atom has. So as a nice little review, hydrogen has 1 valence electron, and I'll use Ve to denote valence electrons. Carbon has 4 valence electrons. We have nitrogen, which has 5 valence electrons. And then we have oxygen, which has 6 valence electrons. So if we were to go through our molecule and count the total number of valence electrons, for this one, I'll go ahead and kind of show the math, but as we go through some of the other examples, I'll just do all the math internally and write it down for y'all so we can see how many electrons we have. But I usually do, especially for doing an exam, I'll put all of my valence electrons in parentheses just so I can easily check my math later on. But we'll first start with hydrogens. So hydrogens have yet again 1 valence electron, which will include our 1 there. And since we have 4 hydrogens, we'll include that in as well. So just to kind of reiterate what the math means, we have 4 hydrogens that each have 1 valence electron each. And then just so we can easily refer back to everything later on, I'll just put an H above those parentheses just so we know what we're talking about there. And then we'll move on to carbon. Carbon has 4 valence electrons, and if we were to check our molecule, we currently only have 2 carbons. So we'll go through and do 4 times 2, and yet again, we are talking about carbon in that case. And then up next, we'll look at the oxygens. Yet again, oxygen has 6 valence electrons, and if we were to do 6 times 2, the 2 is coming from those 2 oxygens, and I'll include the oxygen above. And then from there, we have one nitrogen, and nitrogen has 5 valence electrons. So we'll just do +5, and then we'll put, well, to be consistent, since I did it with the hydrogens, we'll do, oops, 5 valence electrons times 1 nitrogen. Put the nitrogen above it. So if we're looking at this right now, we may think we're all done in terms of finding those electrons, but we have to refer back to those polyatomic ions. So those are going to be our molecules that have a charge. And in this case, whenever we have a negative charge, that means we have more electrons. And then whenever we have a positive charge, that means we have less electrons. And if we're looking at this molecule right here, it currently has a negative charge, which means we need to add in extra electrons. And because of this negative charge, that means we have an extra electron. So we'll go through and add that in. I'll do +1 electron. And if we were to go through all of that math, we currently have 30 electrons. So if we were to go through our steps again, in step 1, we wanted to divide everything by 2. And if we divide 30 by 2, that means we have 15 pairs of electrons. And yet again, the only reason I like to do that is just so it's a lot easier. Yeah, great question. So in terms of dividing 30 electrons by 2, whenever we're looking at bonds or lone pairs, correct? Those are all coming in as 2 electrons, right? So by dividing by 2, we're able to see the pairs of electrons. And when we know the pairs of electrons, it allows us to double check our work later on. And we'll see how we'll be doing that. It just allows us to count the bonds and the non-bonding electrons to make sure we have all the electrons we need for the molecule. Does that answer your question, T? Okay, I'll keep my eye on the chat, but I will keep on moving through the example. So now that we have all of our electrons, we'll now move on to step 2. And for step 2, what I want us to do next is to bond. Thank you. What I'll do next is we'll be bonding the atoms together so each one has an octet. And more specifically, for this example right here, I want to start with the carbons and the heteroatoms first, and then I will add in those hydrogens later on. So we'll start off with our nitrogen, and I'm actually going to rewrite the formula just so it's a little easier to see down here as I'm writing the structure out. Perfect. So yet again, we'll start with the nitrogen. And right now, like I said, we'll be ignoring those hydrogens just for the time being. And our nitrogen is now bonded to this carbon, as that's next in line. And then if we keep on moving left to right, this carbon, which we just wrote down, is bonded to another carbon. And then now we have this carbon being bonded to 2 oxygens. So your first instinct, if we were to keep writing everything down as we previously were, it would be oxygen, oxygen, but that's not the case for in this example. If we were to go through and show the formal charges and everything like that, it would look really weird and we would get a really high negative number most likely. But a little tip I'll give you guys is that whenever we see a COO in a condensed formula like this, what that looks like is something like this. And then I'll just do this since we have a negative charge there. So whenever we have a carbon bonded to 2 oxygens and we see it written out like this in our condensed formula, what that means is our carbon will have a double bond to oxygen, and then it will also have a single bond to the other oxygen. Now, if you're confused right now, I promise you, as we keep on moving through a lot more of our examples and we have a lot more exposures, we'll be more comfortable with these functional groups and a lot of these shorthand notations. So just make sure you keep in mind that in terms of COO, whether it's at the end of a molecule or it's at the very center of a molecule, that's telling us that carbon has a double bond to oxygen, and then the other oxygen will just have a single bond to carbon. So we'll go through, add that into our structure. We have our double bond to oxygen, and then we now have our single bond to our other oxygen. And then since we have all of our atoms in, the nitrogen, the carbons, and the oxygens, we're going to go back and add in those hydrogens. So if we are looking at our formula, we have our nitrogen bonded to these two hydrogens. And you may be asking how we knew it was these two hydrogens and not these two hydrogens. If we were to add these two hydrogens onto this nitrogen, if we were to count the bonds around the nitrogen, yes, R does refer to the rest of the chain. That's probably not something that we're used to seeing in terms of general chemistry, but in organic chemistry, R will be denoting the rest of the chain, just so we don't have to go through and rewrite everything. But yes, these two hydrogens will be bonded to the nitrogen. And then if we were to keep reading, these two hydrogens are bonded to this carbon, and we'll go through and add that in. And then that's all the hydrogens that we need to add in. And then from here, step 3, we're going to add in our lone pairs and assign formal charges. So in terms of adding in lone pairs, the easiest way, in my opinion, is to look at your atoms that don't have a full octet. So for example, if we are looking at this nitrogen, it currently lacks an octet only because there are 6 electrons currently surrounding it. And we know there's 6 electrons because we have 2, 4, 6 electrons in terms of bonds. So if we were to add in a single lone pair, we now have a full octet because we have 8 electrons surrounding the nitrogen. And yet again, just to reiterate, 2, 4, 6, 8. Moving on to the carbon, it has an octet, so we'll keep on moving. And same with this carbon, it also has an octet as well, 2, 4, 6, 8. But now we'll move on to this top oxygen. Oxygen currently right now is lacking the octet because it only has a double bond. And we can think of that as just 2 bonds going towards it. So 2, 4 electrons currently. So if we were to add in 2 lone pairs, here's one lone pair, and then here is another lone pair, oxygen now has an octet. Yet again, just to reiterate, 2, 4, 6, 8. And then lastly, we have this oxygen over here. It currently only has 2 electrons surrounding it. So what we have to do next is add in 3 lone pairs. 2, 4, 6, and we now have 2, 4, 6, 8 electrons currently surrounding that oxygen. Now, there is something special about this oxygen. If we were to refer back to this structure up here, it currently has a negative charge. And if we were to calculate the formal charge of this oxygen, it actually is negative. Any questions on that example? And we'll go over how to find, do bond angles matter when asked to draw just a Lewis structure? I would say it depends on your professor. And the question as well. So if a question says draw a Lewis structure while also representing the bond angles, then yes, definitely include those angles. But in terms of just regular skeletal structures, you don't really need to include the actual angle itself.
And I can jump in here too with that as well. In the very beginning, you're not really going to have to necessarily show so much of Vesper theory as much as you did in Gen Chem. Instead, it's basically going to like quickly jump to the next thing, which is the bond line notation. That's where you see all those lines. And yes, there is still a little bit of Vesper theory there, specifically tetrahedral, that shape, but you won't have to worry too much about like trigonal bipyramidal and all of those, shapes that you were doing before. So for now, I do think it's important to know it because you still can be tested on that for like a quiz in the very first chapter, but you're going to quickly move on in the second chapter and you're not going to be expected to draw it that way afterwards.
Yeah, and that's one of the nice things too about bond line notation is as we're writing everything in bond line notation, the way it's structured is that we're intuitively showing those bond angles. So that's one of the plus sides about bond line notation. And we'll move on to formal charges now, just because we introduced the concept in this example. So formal charge, as a quick overview, it just allows us to keep track of our electrons. I like to think of it as electron bookkeeping. So for example, a negative formal charge means our atom will have more electrons than its valence electrons. And then a positive formal charge means our atom has less electrons than its valence electrons. So an equation you may have seen in general chemistry is formal charge is equal to the valence electrons minus the bonded electrons divided by 2 plus lone pairs. That's too much. So an easy way to remember how to find formal charges is just to have valence electrons minus the amount of lines and dots you have. And the reason we're using lines and dots is because a line, which we can think of as just those bonds, is just your bonded electrons divided by 2. And then lone pairs, those are just your dots. So let's go through what I mean by that little shortcut. So for this next example, we'll show the formal charge of each nitrogen in the molecule below. So if we're looking at this molecule first, we see our nitrogen here. And if we were to refer back to our equation, we have valence electrons minus those lines plus dots. So nitrogen has 5 valence electrons. And then from here, we're going to go through and count those lines and dots. We have 1, 2 lines, 3, 4, sorry, those were dots, 1 and 2, 3, 4, and 5. Those are going to be our lines. And in total, we have 5. So we'll do 5 minus 5, which is equal to 0. So in this case, our nitrogen has a formal charge of 0. Now, moving on to our next molecule, nitrogen is right here. And the number of valence electrons that nitrogen wants will not change. So we'll have 5 valence electrons minus, and then we'll go through counting our dots and our lines. We have 1, 2, 3, 4, 5, 6. So 5 minus 6 is equal to -1. And since we have -1 as our formal charge, we'll go ahead and include that into our structure. And then for this question right here, or this example, nitrogen is in the center. Yet again, it has 5 valence electrons. And if we were to go through and count our lines in this case, we now have 1, 2, 3, 4 lines. So 5 minus 4 is equal to +1. And that is our formal charge. And we'll go ahead and include that into the molecule to represent it. So yeah, that's our shorthand notation of finding formal charges. Any questions? Sweet. I will say, as we keep on going with organic chemistry, I promise you that you don't have to keep using that equation over and over again. As we start doing a lot more practice problems, we'll start to notice a trend in terms of the number of bonds and lone pairs an atom has and what its formal charge would be. So right here is a good chart if you guys want to take a picture of it. And yet again, it's just going over those common trends we see. For example, if we were looking at nitrogen, which we just used in a whole bunch of examples, when it has 2 bonds and 2 lone pairs, it'll have a negative formal charge. And we saw that up here, 2 bonds, 2 lone pairs had a negative formal charge. When nitrogen has 3 bonds, 1 lone pair, it'll be neutral. We saw that in our example. And yet again, 4 bonds, 0 lone pairs, it has a positive formal charge. So just make sure as you're doing the examples, start to notice some of those trends that you see. And I will note that neutral carbon has four bonds, and this will be the most important atom to make sure you're well aware of that trend with. In this example, yet again, we have our structures, but what I want us to do next is to assign our formal charges, especially to the ones that are not neutral. So for example, if we're looking at this carbon, it has a formal charge of 0 because it currently has four bonds. But if we were to look at the left side of that carbon, this carbon right here currently has three bonds. And if we were to refer back to our chart, whenever we have three bonds but zero lone pairs, that means we have a positive charge. And this is what's called a carbocation, which I can go ahead and write down. And a carbocation is when our carbon has a positive charge. And this will be very, very important as we keep on moving further on in organic chemistry. We'll be seeing carbocations a lot, especially when we start talking about reactions. But if we were to assess the rest of the molecule, all of these carbons currently have four bonds, meaning it is neutral. But let's look at this oxygen right here. The oxygen currently has three lone.
All right. So as Cooper comes back, uh, I want to know how you guys are doing with this so far with Lewis structures. Uh, I would say one of the main things is in the beginning, you start to look at these structures thinking, oh, you're back. Okay, great. I was just letting them know that it's super important to know formal charges and to get these patterns because it's going to help them to quickly draw the structure. And then
Mhm.
you won't have to count electrons every single time. You won't have to, figure out the formal charge with that formula. You're pretty much just going to look at it from essentially memory because it's a pattern, just with those main bond patterns, and you'll be able to draw these structures. But Cooper, go for it. Continue with finding the formal charges.
Perfect. Where did I leave off at? I don't
Uh,
know.
I believe it was finding oxygen.
Perfect.
But if you want to recount that real quick,
Yeah.
just to show.
Sweet. So in terms of our oxygen, uh, oxygen currently has three lone pairs surrounding it, and it has one bond, which gives us a -1 formal charge. But we'll go through and just do the math real quick since we did it on nitrogen. I want to make sure we're comfortable with oxygen. Oxygen has six valence electrons. And if we were to count yet again our dots and our lines, we have 1, 2, 3, 4, 5, 6, 7. And if we had 6 minus 7, then that's how we get our -1 formal charge. And moving on to this next one, yet again, if we're looking at all of our carbons, this is kind of what Melissa was talking about of when we're writing these structures down and we're becoming more comfortable, we can look at an atom and easily see what its formal charge is. And in this case, carbon has those four bonds, meaning it's neutral, especially with this one right here. It's still neutral. But if we're looking at this oxygen, it has a positive formal charge as it has three bonds in one lone pair. And yet again, where am I getting that from? It is with this chart up here. And we can also do the math. Oxygen has six valence electrons. And if we were to count our dots and our lines, we have 1, 2, 3, 4, 5. 6 minus 5 is equal to +1. Perfect. Any questions about finding formal charges? Any questions about those examples? Perfect. We'll move on. And in this one, for our next example, what I want us to do is to find the errors in the following Lewis structures. I don't know if you guys have seen questions like this, but I do believe that if you're trying to spot the error of specific examples, that is a good indication that you really understand concepts if you're able to spot what is wrong with a question or whatever it may be. So for these, we'll start on the very left side of the molecule and we'll move towards the right side and try to see if we can find anything that looks a little fishy. But first and foremost, we'll start with this nitrogen charge. Currently, it has a negative formal charge, but like in our previous example, when nitrogen has four bonds, it should actually have a positive formal charge. So we'll go through, kind of cross out that negative charge, and we'll add in a positive formal charge. And we'll keep on moving through the molecule. This carbon looks fine to me as it has four bonds. But if we were to go one carbon over, kind of looks a little weird because we have 1, 2, 3, 4, 5 bonds. And remember, carbon should only have four bonds if it's neutral. Um, we'll say carbon wants four bonds. And in this case, we won't include a formal charge only because this molecule is just, for lack of a better term, wrong. If we were like grading someone's exam paper or whatever it may be, only because carbon does not want to be hypervalent. And what that means is it doesn't want to exceed the octet. So we'll move past that. Just note that carbon only wants it only wants four bonds, does not want five bonds. But we'll keep on moving through the molecule. This carbon currently has four bonds. That's good. This carbon has four bonds. Perfect. And then as of right now, we are showing that this oxygen is currently neutral. But if we were to go through and to find our formal charge, we would have a positive 1 formal charge. Yet again, because oxygen has three bonds and one lone pair, that's one of those common trends we'll be seeing is that when it does have three bonds, one lone pair, we have a positive charge. Any questions on that one? Sweet. Moving on to our next molecule. Right here we have this carbon. And if we were to look at how many bonds the carbon has, it currently has three bonds. And since it has three bonds, it normally wants those four bonds. Since we're lacking one of those bonds, we have a positive 1 formal charge. Yet again, 4 valence electrons minus 3 lines gets us that positive 1. And if we're looking at this carbon, currently has four bonds. It's happy, it's neutral. This carbon as well has four bonds. This carbon too has also four bonds. But what about this nitrogen? The nitrogen has two bonds, two lone pairs, and because it has two bonds, two lone pairs, if we were to go through the formal charge calculations, we would have five valence electrons minus those 6 dots and lines, which would give us a negative 1 formal charge. So now we'll be doing more examples of drawing Lewis structures in their entirety. And one of the things I will note is we may be used to molecular formulas, but in organic chemistry, we'll be introduced something that's called a condensed formula. So the main difference is that a molecular formula shows the atoms. So for example, if we're looking at C5H12, that's telling us that we have 5 carbons along with 12 hydrogens. But if we're looking at a condensed molecular formula, just a condensed formula, that is showing us the bonding. So as we're reading this, it shows us how those carbons are actually bonded to each other, as opposed to a molecular formula. That's just telling us how many atoms we have. So for our next example, we're going to go through and draw the Lewis structure for the given condensed molecular formula. So if we were to go start with step 1 of how we normally should approach these Lewis structures, if we were to go through, we have 22 electrons. And if we were to divide that by 2, we have 11 electron pairs. And then moving on to our second step from earlier, we want to go through and just have those carbons be bonded to each other. So in this example, we have 1, 2, 3, 4 carbons. we'll go through, show those carbons bonded to each other. And in this case, we are being shown how the atoms are actually bonded. And that's what we were talking about earlier with our first example. So we have these two hydrogens being bonded to this carbon right here. And then if we were to look at our next carbon, which is shown right here, it's currently bonded to one hydrogen. We'll add that in. And then same with our next carbon, which is right here. It is bonded to the hydrogen right next to it. Add in the hydrogen. And then our last carbon has two hydrogens bonded to it. And since we're only dealing with carbons and hydrogens, and we have a neutral molecule, which means overall has a charge of 0, we know that we're going to have no lone pairs. And this is why, in my opinion, it's important to know the pairs of electrons that you have in a molecule. So for example, we have 11 electron pairs. So if we were to go through and to count our bonds, we should have 11 bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this case, we're missing some bonds. And if we were to look at our structure, some of the carbons don't have those 4 bonds, which is our main goal to have. So this is where some of those double bonds will come into play in terms of us adding in extra bonds so that the carbons can be happy with 4 bonds surrounding it. So what we can do is we'll add a double bond here and a double bond here. And by doing that, if we were to go through and check all of our carbons, this carbon has 4 bonds. So does this one, and this one. I will note, because I know there may be some point of confusion, just say if we were to add a double bond, or sorry, if we were to add those double bonds right next to each other, the reason that would be incorrect is because if we were to count the total number of bonds this carbon has, it currently has 1, 2, 3, 4, 5 bonds. So that's why we spaced those double bonds apart, just so all the carbons only have 4 bonds. Any question with that one? Perfect. And then from here, we'll just keep on drawing some Lewis structures. So for our next one, we have our molecule right here, and we have to note that it does have a -1 formal charge. And if we were to go through and count our valence electrons,
If you can read the question as well.
yeah. So our question says, kind of off topic, but the CH3, CH2, CH3, 2 formula is the first, they're asking, is the first CH3 considered a methyl group? I know the CH3 is, but I was curious about the first CH3 in the condensed formula. Is this one of the later examples I have, I believe? Oh, okay, sorry, right here. Perfect. That's what you were talking about. Yeah, so if we're looking at this one right here, that first CH3 group, that is also a methyl. And then what these parentheses mean right here, that's telling us that we have 2 methyl groups coming off of this carbon right here. So yes, whenever you have a CH3, that's telling us we have a methyl group. And in this case, I know it may be a little confusing because of those parentheses, but it's telling us that we have 2 methyl groups, instead of 2 is on the outside of the parentheses. So these 2 methyl groups are bonded to this carbon. Does that answer your question? Of course. So we'll go back to this example. But yeah, if we were to go through and count our valence electrons, we would have 9 valence electrons. But yet again, since we have a -1 formal charge, we need to add in that extra electron, so plus 1 electron. which means in total we have 10 electrons. But if we were to divide it by 2, we have 5 pairs. So from here, we'll just have carbon bonded to nitrogen. And this is where it may get a little tricky in terms of knowing where that negative charge goes. But since we're only allowed 5 electron pairs, what we can do is add in a triple bond there between the carbon and nitrogen. And then let's see what happens if we were to add one lone pair onto both carbon and nitrogen. So if we were to go through and count the formal charge, nitrogen has 5 valence electrons. So if we were to do the 5 minus the dots and lines, we have 5 minus 1, 2, 3, 4, 5. So our nitrogen will be neutral. But then in terms of carbon, if we were to go through, we have 1, 2, 3, 4, 5. 4 valence electrons minus 5 dots and lines gives us a negative formal charge. So that's where the negative formal charge on carbon is coming from. And you may be questioning, why is the negative charge only on carbon and not nitrogen? And the reason behind that is because if we were to force the negative charge onto nitrogen, uh, the number of electron pairs we would need in the molecule wouldn't add up. And yet again, that's just another point in terms of why we should look for those electron pairs, just so we can always double check our work later on. But we'll move on to this example. So for this one, what we can do is add up yet again our valence electrons. And if we were to add up our valence electrons, we would have 25 valence electrons. But in this case, we have a positive 1 formal charge. So remember, whenever we have a positive charge, that means we have less electrons, right? So we're losing an electron, which is why we get that positive charge. So we'll actually do minus 1, which gives us, oops, I think I did my math a little wrong. That gives us 27 valence electrons. Yes, we have 27 valence electrons minus 1 electron, yet again, because of that positive charge, which gives us 26 electrons. And if we were to find our pairs, divided by 2, and that gives us 13 pairs of electrons. So let's go through our condensed formula and see how everything is bonded. So we will first start off with our CH3 group. And for this one, I'm going to start to add in those hydrogens with our carbons and our heteroatoms as well, just so we can get more comfortable with that. So we'll do carbon has 3 hydrogens bonded to it. And our carbon is now bonded to this oxygen right next to it. So we'll go through, add that in. And if we're looking at what this oxygen is bonded to, this is going back to those parentheses we just talked about. The parentheses is telling us how much of a specific group we have. And this CH3 group is what's called a methyl group. And the parentheses are telling us that we have 2 CH3 groups that are bonded to this oxygen. So let's go through and add in those CH3 groups. And as I'm doing this, we'll soon realize why bond line notation will become your best friend, is because you won't have to write out all of these Lewis structures, and it'll be a lot more simpler. But from here, let's go through and double check our work. We should have 13 electron pairs, and we currently have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if we were to look at this oxygen, it's currently lacking the octet. And if we were to go through, add in a lone pair right there, we now have a full octet around the oxygen. And this is where it showcases that positive charge. Because if we were to go through, calculate the formal charge on that oxygen, it gives us a positive charge. Perfect. And then up next, we'll go through this example right here. And if we were to count the total number of valence electrons, it has a lot. We have 38 valence electrons. And if we were to divide that number by 2, we now have 19 pairs of 19 pairs of electrons. And let's just go through and work through our condensed formula. So our first atom we'll start with is our carbon. And in this case, I definitely want to add in that methyl group, that CH3 group at the end, just so I can visually see where the end of the molecule is. And then now we have to look at the parentheses again. Um, in this case, since we have the parentheses in the very middle of the molecule, especially like this, it's telling us that we have four CH2 groups that will be back to back to back. So let's go ahead and draw that out, and then we'll refer back to the parentheses. So since we have four in our parentheses, that means we have four carbons if we kind of multiply that through the parentheses. So 1, 2, 3, 4. Perfect. And then from there, we can just add in our CH2 groups, sorry, the hydrogens. 1. Perfect. And then yet again, this is just a good visual representation of what that 4 means on the outside of the parentheses of that CH2. So we have our 4 CH2 groups right there. And then at the very end of the molecule, we have our OH group, which is what is called our alcohol group. Perfect, added that in. And then if we were to go through and count our pairs of electrons, we currently only have 17 pairs of electrons. And if we wanted to have all of the electrons we needed in the molecule, we can include some lone pairs on our oxygen. And as of right now, we only have 2 bonds on oxygen. So if we were to add in 2 lone pairs, oxygen now has an octet. And most importantly, it is neutral. And up here, our molecule is also shown as neutral. So that works out. Any questions? Perfect. We'll move on to this one. If we were to count our valence electrons, we have 40 valence electrons. So the 40 divided by 2, we're finding our pairs of electrons. We have 20 pairs of electrons. And we'll just keep on going through the molecule. On the very end, we have our methyl group, our CH3 group. So we'll go through and include that. And then our carbon here is bonded to this carbon. And this carbon is bonded to this carbon. So we added in 2 carbons so far. I might move this over to give us some more room. And then now we're running into the parentheses again. If we're looking at the outside of the parentheses, we have a 3. And yet again, just to remind you, that's telling us we have 3 CH2 groups. So we'll add in 3 extra carbons. And then I'm going to add in just a CH right there, just so we can visually see where our parentheses are starting. After today's session, you'll be thankful that you guys learned bond line notation next week. And then we have our 3 CH2 groups that we just added. And then at the very end, we have a methyl group, which yet again is at CH3. So perfect. If we're looking at the molecule, everything looks good except this section right here. Now, if we're looking at our carbons in terms of these two, they currently only have 2 bonds each. And yet again, if we only have 2 bonds, that means we're lacking the octet because carbon wants 4 bonds. So since we are lacking bonds, we need to include some more. And what we can do is we can have a triple bond between those carbons, sorry. And by adding in that triple bond, this carbon is now happy because it has a total of 4 bonds. And then same with this carbon. It's now happy as it has 4 bonds. And if we were to go through and count our pairs of electrons, we would count 20 total bonds. And then next week as well, we'll be going over a lot more in depth in terms of double and triple bonds as well. And then we'll go through and finish up our last couple of Lewis structures. Yet again, for our next one, we have a lot of valence electrons. We have 66 valence electrons, which is a lot. 66 divided by 2 gives us 33 pairs of electrons. And then from here, we'll just keep on reading our formula and work through the molecule. In this case, though, our parentheses are on the end, and we have 3 CH3 groups. Now, we can't have CH3 groups continuously bonded back to back to each other, just like we have with these CH2 groups, only because of formal charge. If we had those CH3 groups um, bonded to each other back to back to back in terms of 3 times in a row, we would end up having too many bonds to carbon. So what this is telling us is that we have 3 CH3 groups bonded to the carbon that's right next to it. So we'll go through and draw out this carbon right here. And this carbon is bonded to 3 it's bonded to 3 CH3 groups as we're shown by these parentheses. And as a shorthand notation, since this molecule is going to get really big, I will write down CH3, and hopefully that helps you see what those parentheses actually mean. So we have CH3 number 1, CH3 number 2, CH3 number 3. So we have all of our CH3 groups bonded to this carbon, and we see that this carbon is bonded to the carbon on the right of it. And then from here, we have a CO2 group. What does that mean? If we remember from earlier, we did have a CO2 group, but it was just written as COO. And if you remember back to what COO means we have carbon that has a double bond to oxygen and also has a single bond to the other oxygen. So we have both of our oxygens here that we have up in our condensed formula, which is nice. And if we were to keep reading through the formula, we'll go towards the right. The next thing that the oxygen is bonded to is going to be another carbon. So we'll add in our carbon. And then just for reference, this carbon right here is the one that I just drew out. And then we're back to the parentheses. We have 3 CH3 groups that are going to be bonded to this carbon. So we'll do exactly what we did for this group. We'll just add in CH3 as a shorthand notation. And there we go. We have our 3 CH3 groups bonded to this carbon. Perfect. And then from here, we need to add in our lone pairs. And if we're looking through everything, oxygen is currently lacking an octet, but if we were to go through and add in our lone pairs, that's how it can achieve the octet. So this oxygen up here only has 2 bonds in the form of a double bond, which means if we were to add in 2 lone pairs, oxygen is now happy, it has that octet. And then same with this oxygen right here, currently only has 2 bonds, so we need to add in 2 more lone pairs, and then it's now happy with the octet. We'll just jump right into the next one. So we won't start with the hydrogen first. We'll start with our carbon just because hydrogens only bond to one atom, only has one bond, sorry. So we'll start with our carbon. We'll see what our carbon is bonded to. It's bonded to the hydrogen on the left, so now we can include that. Push that off to the side. Perfect. And then this carbon is now bonded to our oxygen, which we can just put up here. And then in terms of how we're reading it, I know that for these previous examples, we've been reading everything left to right. And if we were to add in a nitrogen like that, yet again, if we added in those lone pairs later on, our formal charges would not be what they should. So in this case, what we can do is we can have a double bond to oxygen. So this carbon actually has a double bond to oxygen, and then we can have the nitrogen bonding to the carbon since we need 4 total bonds for carbon in general. So yet again, we can't just have oxygen bonded to nitrogen because if we were to add in those formal charges, wouldn't really add up. So we'll have a double bond from carbon to oxygen, and then single bond of carbon to nitrogen. And then we see that nitrogen has a bond to a hydrogen, which we can see here, and H. And then our hydrogen can't be bonded to a CH3 group because if we remember, hydrogens only want one bond. So our CH3 group can only be bonded to that nitrogen, which we'll add in. Again, we'll just use that shorthand notation just to make it a little smaller. And then from there, we'll add in our lone pairs. This is where we start seeing that trend after a couple of those carbon double bonds to oxygen, is that whenever we do have a carbon double bonded to oxygen, we'll include, our two lone pairs. And by doing that, oxygen is now neutral. And then from here, if we're looking at nitrogen, we don't have a full octet. We need to go through and include those lone pairs. And now nitrogen has 8 electrons currently surrounding it. Any questions on those Lewis structures? Perfect. So the next thing we'll dive into quickly are polar covalent bonds. And if we're looking at these two molecules, there is a bit of a difference. Yes, we have an OH group on the right side on this right molecule, and we don't have it on the left group. But most importantly, this molecule is what is considered nonpolar. But this molecule over here is polar only because we added in that OH group. And we'll talk about what polarity and dipoles are in just a second. But in order to review those, we need to understand electronegativity. So electronegativity is an atom's tendency to pull electrons towards itself. So yet again, if we have a highly electronegative atom, it's really grabbing onto those electrons. It has a high attraction to kind of suck them in towards like its nucleus, if you want to think about it that way. Think of it as like a magnet. The more electronegative it is, the stronger the magnet, just kind of pulling in those electrons. And if you remember the periodic trend from general chemistry, it will increase moving left to right. So if we start on the left side of the periodic table and move towards the right, electronegativity will increase. And then if we start on the bottom of the periodic table and moved all the way up to the top, it will increase as well. And do note that this is the opposite of atomic size, which is something that is interesting. They will be inversely related to each other. So in this case, for our next example, we'll just go through and identify any partial charges in the molecule. So what we want to do is find those atoms that have a difference in electronegativity. So if we're looking at our carbon-carbon bonds, we don't really have any difference in electronegativity just because they're both carbons. If we're looking at the carbons and hydrogens, those have a very, very minor difference. So we'll just let those be. We'll ignore those for now. But the main thing we're going to look at is our OH group, our oxygen. So oxygen, if we were to refer back to our periodic table, is right here, and it's kind of on the far right and almost on the very top of it. So it is decently electronegative. So since it is a lot more electronegative than both carbon and hydrogen, it's pulling those electrons closer to itself, which gives it a partial negative charge. And that's what this symbol right here means. I'll redraw it. That is a partial negative charge. So it's not a full negative charge, but it's pulling those electrons towards itself so strongly to where it feels like it has a small negative charge, hence the partial negative charge. And since this oxygen is kind of stealing electron density between this carbon-oxygen bond, because carbon is less electronegative, it's kind of like a game of tug-of-war between carbon and oxygen, but oxygen is a lot stronger, so it's stealing those electrons from carbon. We'll be giving carbon a partial positive charge, and then same idea with this hydrogen. Oxygen is winning that game of tug of war, so it's stealing those electrons from hydrogen, giving it a strong partial positive. So those are our partial charges there in terms of that structure. But we'll go through and move over here. So if we're looking at our atom, we'll look at nitrogen since it's on the left. If we were to refer back to our periodic table, it's decently electronegative since it's closer to the top right portion of the periodic table. So nitrogen, yet again, since it's more electronegative, it's pulling those electrons closer to itself. So we'll give that a partial negative charge. And what it's doing is it's pulling that electron density away from the hydrogens and the carbon. So our hydrogens will get a partial positive charge along with our carbon. And then from there, we'll move over to our oxygen up here. And it's pretty easy to find our partial positive charges because we're looking for those heteroatoms. So nitrogen, oxygen, whenever we see those, that's kind of a good indication that we'll be dealing with partial charges. And then we're just following the same trend. Oxygen is more electronegative than carbon. We'll go through, add in that partial negative charge, and then carbon is less electronegative, so we'll add in that partial positive charge. Sweet. And then in terms of us being comfortable with electronegativity, the reason we want to be comfortable with it is yet again, just so we can find those differences in electronegativity. And those differences cause a withdrawal of electrons, which create those partial positives that we were just talking about. And that is what's called induction. So the greater the difference in electronegativity, the larger those partial charges. So for this next example, I'm just going to plug in my laptop real quick. Perfect. For our next example, we're going to see which carbon has the greatest partial positive charge. And in order for us to do this, did you have a question, T? Oh, that was the answer, the OH. Perfect. Yes, you are on the right track. But we'll go over why this one is or will have the greatest partial positive charge. But in terms of the greatest partial positive charge, we need to see which atom is most electronegative. So if we were to go refer to our periodic table up here, bromine is down here, and our other atom was our magnesium because that is directly bonded to our carbon. Magnesium is all the way over here on the left, meaning it's not that electronegative if it's just not in general. So bromine's here, magnesium is here, but then oxygen is all the way up here. So it's way more electronegative than both magnesium and bromine. And since it is way more electronegative, it's pulling the electrons away from carbon more strongly. So it gives carbon the greatest partial positive charge. Any questions on that one? Perfect. And then we'll move on to this example. We only have a couple more guys, I promise. For this one, we'll identify any partial charges in the molecules below, but then I want us to see if the entire molecule is polar or not. So what we need to do is to go ahead and include our partial charges. So carbons, we have those bonded to chlorines. Chlorine is more electronegative than carbon, so it'll be pulling electrons away from it. So we'll give those chlorines a partial negative charge, which forces our carbons to have a partial positive charge. And then in terms of seeing if the entire molecule is polar, we'll wait on that for just a hot second. And we'll note that this molecule is similar to this one over here, but those carbon-chlorine bonds are facing opposite directions. But since we're dealing with the same atoms, chlorine will have a partial negative charge, same with the other one. And then this carbon, or both of them, I should say, will have partial positive charges. And what we need to do here in order to decide on if the entire molecule is polar is we need to include those dipole moments, meaning what is the direction that those negative charges or those electrons are being pulled from. So that's what we're going to use. This notation will include an arrow, which has a line at the very end. And the arrow will be where our negative partial charge is. And then this side over here is where our partial positive charge will be. And the one way I remember that is I think of this side over here as a plus sign, since it looks like it if you draw it out like that. So if we were to draw in our dipole moments, we'll do it in purple. Our partial negative charge is on the chlorine, so the electrons are being pulled towards the chlorine, and we'll include it on the other side as well. Perfect. And then we'll include it on our other molecule over here. Electrons are being pulled towards chlorine, but now we see a difference. So if we're looking at this molecule over here, we have a net dipole on the same side, meaning the electrons are being pulled all the way over to this side of the molecule. As opposed to this structure over here, we have a dipole going this way, and then we have another dipole going the other way, these same atoms with the same differences in electronegativity. Now, we have to remember that when we're dealing with dipoles, that those are considered vector units. And if you forget what vector units are, that just has to deal with the direction. And in this case, we can think of our up direction. Anything that's pointing up here is our positive direction. And we can think of anything down here as a negative direction. So since both of these are facing in the positive direction, we can think of this entire molecule as overall polar, which we'll write down, as our net dipole is facing the same way. But then over here, we have this carbon-chlorine bond. The net dipole is facing towards our quote-unquote positive direction. But then this net dipole is facing towards the quote-unquote negative direction. And since those net dipoles are facing the opposite directions, they actually cancel each other out, which renders the entire molecule as non-polar. So that's just one thing to keep in mind, is that when we're talking about our dipoles, they are vector units, meaning that the direction of them matters. And then I believe we have one more example. For this, we're just going to identify the net dipoles for the following molecules. And for these two, they should be decently easy because we're looking at the most electronegative portion of the entire molecule. And we're seeing how the electrons are being pulled towards that portion. And if we're looking at this structure, this is a good hint at bond line notation, that these are all carbons down here. And we have our most electronegative portion with that oxygen all the way up here. So our net dipole will be towards the oxygen since it's the most electronegative atom in the entire molecule. And then very similar onto this side over here, we have all of our carbons, but we have this part of the molecule, we have our oxygens. Oxygen, more electronegative, so our electrons are being pulled towards the oxygens. So that's our net dipoles. And then lastly, I just wanted to do a quick review on the differences between covalent bonds and ionic bonds. We touched on it earlier that covalent bonds are bonding electrons that are being shared between two atoms. So yet again, we have this carbon that is sharing electrons between the hydrogen it's bonded to. But then if we're looking at ionic bonds, this is where a huge difference in electronegativity comes into play. And that difference is so great to the point where the oxygen, for example, can just steal the electron from a sodium, from a sodium atom. And when it steals that electron, it gives the oxygen a full negative charge, and then it gives the sodium a pure positive charge. So that's when our electrons are completely stolen. And then as a quick tip, normally, as like a good helpful hint, whenever you see a metal atom, that means a lot of the times that it will be an ionic bond. But from there, that wraps up the first week of tutoring. I'm happy you all joined. And in terms of next week's topics, we'll be diving into bond line notation, kind of going over a way easier way as opposed to Lewis structures of how we can draw molecules. And then we'll also review some of the atomic orbitals and how those atomic orbitals can come together to form hybridized orbitals. And all of those will lay a huge foundation for all of organic chemistry.
Thank you so much, Cooper. Big thank you to you for explaining all of those topics. And guys, there is going to be another weekly live tutoring on Monday for organic chemistry. Cooper, again, will be leading this. He'll be covering these topics. I highly recommend stopping by and even rewatching this. That's going to be important. I'm also going to put in the chat right now other places, other things to review before your class starts. So this is the link. Mainly it's because your professor is going to expect that from you already walking in day one. So make sure to review that. And it's going to be at the same time the live stream for next week. We'll keep posting that and making that announcement, whether it's email, YouTube, or really everywhere on community as well. So just letting you know, thank you again so much for being here. We're excited to start this semester off right. And let me know if this was helpful. Let us know what you liked. I see some claps. Thank you, Caitlin. Was this helpful? Okay, I see some hearts. Thank you as well.
Thank you.
Yeah, wonderful. We're getting a bunch of thank yous, and really, I know this is going to be helpful walking in. You're going to feel like you're more ready, especially even from your classmates because they didn't do this review. So we're starting off right, and great.